I begin this story not with a flare, but with silence. 8 minutes of it. That is how long sunlight takes to travel from the surface of the sun to Earth, a fact measured since the 19th century and refined by modern spacecraft timing. In those 8 minutes, nothing we do on Earth can change what is already on its way. That delay is the central tension of everything that follows. Picture a quiet morning in low Earth orbit. Satellites slide above the blue curve of the planet at 7 kilometers per second. Below them are power grids, pipelines, GPS signals, aviation routes, and undersea cables that quietly hold modern civilization together. From space it looks calm. The danger is invisible, and that is why it matters. Within your first 3 minutes with this episode, if you value calm, source-based space science, please consider subscribing to CosmoQuest 88. The sun is not a steady lamp. It is a magnetized, boiling sphere of plasma whose magnetic field twists, tangles, and occasionally snaps. When that happens, the result can be a solar flare, a coronal mass ejection, or both. A flare is a sudden burst of electromagnetic radiation across the spectrum. A coronal mass ejection is a massive cloud of charged particles hurled into space at millions of kilometers per hour. These are confirmed phenomena observed directly by missions such as NASA's SOHO, Stereo, and the Parker Solar Probe, as well as by NOAA's space weather satellites. Most days, the solar wind is gentle enough that Earth's magnetic field deflects it with little consequence. The magnetosphere acts like a vast shield, compressing on the sunward side and stretching into a long tail behind the planet. This structure has been mapped for decades by spacecraft like ACE and DS-COVR positioned at the L1 point between Earth and the Sun. That is confirmed physics. The problem arises when the Sun produces an unusually powerful eruption. In 1859, a storm now known as the Carrington event disrupted telegraph systems worldwide, ignited sparks in equipment, and produced auroras as far south as the Caribbean. That historical record, supported by geomagnetic measurements reconstructed from magnetograms and ice core data, remains our best evidence of an extreme solar storm impacting Earth. It is not myth, it is the benchmark for risk. Today, our vulnerability is different. Telegraph wires have been replaced by satellites, fiber networks, and high-voltage transformers that are far more sensitive to geomagnetic disturbances. When a strong coronal mass ejection hits Earth, it can induce currents in long conductors like power lines. This is not speculation. In 1989, a geomagnetic storm triggered a 9-hour blackout across Quebec, Canada, by damaging a major transformer. That event is well documented by Hydro-Quebec and space weather agencies. Here is where I separate what we know from what we suspect. Confirmed. Intense solar storms can damage satellites, disrupt GPS, disturb radio communications, and stress power grids. Confirmed. We have monitoring systems that give us between minutes and a few days of warning, depending on where an eruption originates on the Sun. Hypothesis. A truly extreme event comparable to or greater than Carrington could cause multi-day or multi-week outages in some regions. Unknown. Exactly how modern, interconnected grids would behave under such stress at global scale. The science of forecasting space weather is improving but still incomplete. Instruments like NASA's Parker Solar Probe are flying closer to the Sun than any spacecraft before, sampling the solar wind directly and revealing how magnetic turbulence develops. Meanwhile, solar observatories such as NASA's Solar Dynamics Observatory watch the Sun continuously, mapping magnetic regions that are likely to erupt. We can see danger forming, but we cannot prevent it. Time matters. A fast coronal mass ejection can reach Earth in as little as 15 to 18 hours. Slower ones may take 2 to 3 days. That window is what emergency planners rely on. It is enough to shut down sensitive systems, reorient satellites, and reduce loads on power grids. But it is not enough to rebuild infrastructure. There is also a quieter risk: radiation. High-energy particles from solar storms can increase radiation levels at high altitudes, affecting astronauts, airline crews, and even electronics on some aircraft routes. Space agencies track this carefully, and airlines adjust flight paths when necessary. This is routine risk management based on real data, not alarmism. Now I want to focus on the chain of cause and effect. Solar eruption leaves the sun. Particles race through interplanetary space. Earth's magnetic field intercepts them. The field compresses and reconnects, releasing energy into the upper atmosphere. That energy drives brilliant auroras near the poles and electrical currents through the ionosphere. Those currents, in turn, can induce voltages in ground-based infrastructure. Each step is well studied, but small uncertainties at each link can amplify into big differences in outcome. This is why scientists talk about resilience rather than prediction. We cannot stop the sun from erupting, but we can design systems that fail gracefully instead of catastrophically. Modern grids increasingly use sensors to detect geomagnetic disturbances in real time. Satellites carry radiation-hardened components and safe modes that protect critical instruments. These are practical, evidence-based adaptations. At roughly the midpoint of this story, the central message is simple and grounded. Please like this video and subscribe to support CosmoQuest 888. Beyond infrastructure, there is a deeper scientific question. Why does the sun produce extreme events at all? The answer lies in its magnetic dynamo, generated by the motion of electrically conducting plasma inside the star. We observe an approximately 11-year solar cycle in sunspot activity, but the timing and strength of individual storms remain partly unpredictable. This is a frontier of heliophysics, actively studied by missions like Parker Solar Probe and ESA's Solar Orbiter. Some researchers hypothesize that extreme events may be more common than historical records suggest, based on traces found in tree rings and ice cores that show spikes in cosmic radiation known as Miyake events. These are still being investigated, and linking them directly to specific solar eruptions remains an open problem. That uncertainty is honest science, not a weakness. From Earth, the practical takeaway is measured caution. We should expect solar storms, prepare for them, and avoid panic. Space weather is not an apocalypse. It is a natural hazard like earthquakes or hurricanes, governed by physics we are gradually understanding. I return to that initial image of satellites sliding silently above Earth. They are our eyes and nerves in space, but they are also exposed. A single powerful storm could temporarily blind some of them, forcing us to rely more on ground-based systems. That fragility is real, and acknowledging it is the first step toward resilience. At the same time, there is beauty here. The same processes that threaten our technology create the auroras that paint polar skies in green and red. Energy from the sun becomes light in our atmosphere. Risk and wonder share the same origin. As this episode nears its end, I want to be clear about what remains unknown. We do not know when the next Carrington-level event will occur. We do not know exactly how modern infrastructure would respond at global scale. And we do not know whether our current warning systems are sufficient for every scenario. Those uncertainties are why continued investment in solar monitoring matters. Missions like Parker Solar Probe, Solar Orbiter, and future space weather satellites are not luxuries. They are insurance policies based on physics, data, and experience. They shrink the gap between what the sun does and what we can anticipate. About 1,000 characters from the end of this script, I pose a single practical question. If you had to choose, would you invest first in better space-based solar monitoring or in hardening ground-based power grids, and why? If you want more calm, evidence-driven episodes like this, please subscribe to CosmoQuest 888. In the end, solar storms are not a battle between the sun and Earth. They are a relationship between a star and a planet that has learned to watch it closely. The light that sustains us also carries risk, and understanding that balance is the real story of space weather.